we are going to try to use JWST to understand the origin of the heaviest elements in the periodic table. So how are we actually going to do it? It's going to be a bit of a whirlwind story for the next 20 minutes that involves merging neutron stars, gravitational waves, and some of the most energetic explosions in the universe. But let's take a step back first. There are about 3 different points I want to hit on in this talk. The first is just giving you some background to understand why it is still uncertain exactly where the heaviest elements come from. I'll give you a little insight on what gravitational waves have to do with any of this, and then, of course, what JWST can do. But I also want to emphasize that this proposal, I didn't list everyone on the slide. Maybe I should have tried, but this is a proposal which was a collaboration of over 70 scientists worldwide. It's one of a number of proposals that are trying to do science with JWST by studying light that is associated with explosions that are also found in gravitational waves. So this is just one slice of the science that we can do with that sort of observation. But there are a huge number of people involved in this science. But if we want to focus in on where do the heaviest elements come from, I might just start with this quote, which hopefully most of you are familiar with, from Carl Sagan, describing that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. So this is an incredibly poetic quote, but it's also really nuanced. It turns out there are tons of different ways that stars can make elements, and there's actually still quite a bit of debate on the heavy end of the periodic table. So here is the periodic table. When I say there's this debate at the heavy end, what am I talking about here? Which elements am I actually describing? Well, it turns out that we know things like we're pretty sure that the hydrogen and the helium in the universe, even things like most of the lithium and the beryllium, were actually formed in the Big Bang itself, when the universe was just a soup of primordial particles that were cooling over time. We also are pretty sure that things up to what we call the iron peak, so things like iron, cobalt, and nickel, are formed either in normal stellar cores or, most commonly, in supernova explosions. However, that actually doesn't get us very far. If you look at the periodic table, there's still a ton of things in this grayed out region that I haven't mentioned yet. And a lot of these are very important. From the typical press release, I'm obliged to tell you that gold is involved in this. We don't actually know where gold comes from specifically, but there are also some other things that are very important in our daily lives. Things like neodymium, which is really important for magnets, which are found in almost all our electronics. And then even more particular to this crowd, you have things like all of mercury, cadmium, and tellurium, and even arsenic are in this grayed out region right now. And those are critical for all the detectors in all 4 JWST instruments. So we are talking about those elements and trying to understand where they actually come from. So it turns out there are a few options, but it's worth spending a minute talking about how we think you even make these heavy elements, because that will be critical for understanding the astrophysical sites that could lead to them. So the reason that I stopped here at the iron peak up to now is that past that, you no longer gain energy by just fusing together smaller elements. If you take 2 hydrogens into helium, you get energy out. But once you get up to iron, that is no longer true. It would take energy to fuse together heavier elements. So we actually need a different physical process than standard fusion to get up to a majority of the elements in the second half of the periodic table. So what is that physical process that actually allows us to get past this point where you would need energy to nominally go further? So how do you make those heavy elements? There's one critical piece of physics that you need to link onto to understand this process, and that is that especially when you have particularly large nuclei, there's a non-zero probability that a given neutron in the nucleus of that atom will spontaneously undergo a beta decay. And when that beta decay happens, down here it's shown in the lower portion here, that neutron, it will turn into a proton, emitting an electron and a neutrino in the process. But that fact that the neutron turns into a proton is critical because that's basically a way where you can change what element you are and actually move one element up the periodic table if you turn a neutron into a proton. So here is a, unfortunately low resolution, but animation of what this might look like. So the things that you should hold on to is over here on the right-hand side. This is showing the number of protons in this nucleus, the number of neutrons, and therefore what element this actually is. So when you're undergoing this process of capturing a neutron and then undergoing a beta decay to make heavier elements, it might look something like this. You have these blue things are the neutrons, so you have a couple of them joining. So you see the neutron numbers going out, but the element hasn't changed because that's just tied to the proton. But then one of those neutrons just underwent this beta decay, at which point your proton number ticks up, and now you have cobalt. So that's the idea. And this is easier than just fusing elements together because the neutrons don't have charge. So it's not easy, but it's a little easier for them to shove their way into the nucleus of an atom. And therefore, we can slowly inch our way up the periodic table. Turns out this process can happen either slowly, where you just sort of slowly add in a couple neutrons, maybe a neutron every 10 to 100 years into a nucleus, and then it will beta decay. So it'll slowly meander its way up. That's called the slow process or S process. But there's another physical mechanism where this could happen incredibly rapidly, where you literally start bombarding nuclei with hundreds of neutrons per second and start undergoing this neutron capture way of creeping your way up the periodic table. So here's one more animation that tries to illustrate for you a little bit of what this might actually look like, especially with this rapid process. So what's going on in this plot is we have on the horizontal axis just the neutron numbers, how many neutrons are in the nucleus of an atom, and then on the vertical axis, the proton number. So higher up on the vertical axis, that's a heavier element. So when we're trying to work our way up and make heavier elements, we're trying to get further vertically on this plot. And the colored squares in this are going to represent, this is actually the results of a numerical simulation that was run by Stefan Roswag. And all of the colored dots are showing you in this simulation what elements are present. And he's basically going to start bombarding it with a high flux of neutrons and seeing what happens to the elements. So when this happens, how you should just interpret this plot is that if you undergo a neutron capture, you are going to move horizontally to the right because your neutron number goes up, but not your protons. And then when this beta decay happens, you sort of move backwards and diagonal up this way. So you sort of gain in the vertical axis, and you are now a heavier element. So that's how you should watch the colored dots in this animation. So when we do this, it sort of starts with a certain set of elements, and then you can see it sort of moves around a bit, and then they slowly get to the process where they're gaining a lot of neutrons, so shooting to the right, and now they're going to undergo these beta decay to get back to a region where the elements are a little more stable. That's what that black line is. So I'll show you it one more time, and pay attention to this plot in the lower right, which is just showing you what elements do you have a lot of abundance of. So at the beginning, we have some heavy elements. But as we go on, you're going to be gaining a bunch of neutrons. And then as you undergo this beta decay back down to more stable elements, you end up with a distribution of elements where you now have much heavier elements than you started with. So this is how we can inch our way up the periodic table. So that was a bit just about nucleosynthesis and how you get there. It turns out that we know from studying abundances and isotopes in meteorites here on Earth that this rapid process where you actually bombard nuclei with hundreds of neutrons per second must actually occur in the universe. About half of the very heavy elements in the periodic table have to come from this process. So then the question we have to ask ourselves is, what is the astrophysical site? Where do those physical conditions exist where you're going to be bombarding nuclei with hundreds of neutrons per second? This is clearly a very energetic process. So we are going to be looking at some of the most energetic events that actually occur in the universe, which is where my expertise in astronomical explosions come in. So there are a couple of options for this. The first is just your run-of-the-mill supernova explosion. These are very energetic. Pros of this is that they are actually very common. Stars that are 10 times more massive than our sun explode all the time in the universe. So you would not actually need an individual supernova to produce very many heavy elements to make this the dominant source of those elements in the periodic table. However, a con is that theoretically it's not actually clear that the right physical conditions exist in supernova, that you actually get this soup of bombarding hundreds of neutrons per second on your nuclei. So it's not clear it can actually do it. So what's another option? Another option is neutron star mergers. So neutron stars are just what is left over themselves after a normal supernova occurs. And if two of them are close enough together, they can eventually tear each other apart, throwing out material in the process, like what you just saw in this video. The pros to this are that the conditions are great. These are neutron stars. They're made of neutrons. All of the material thrown out in this explosion is just a soup of neutrons with very high energy. So we know that the physical conditions should be right. The con is that these events are incredibly rare. You need 2 supernovae to happen to get your 2 neutron stars. You somehow need the binary that those stars were formed in to not disrupt after going through those 2 explosions, and you need them to be close enough together that they will eventually merge. So they're very rare. And so it was not clear that there were enough of them or that they made enough to explain the heavy elements we see in the universe. So we have these 2 options. How can we as astronomers, I'm an observer, actually try to observe the elements that are created and try to understand if they are making these heaviest elements in the periodic table? There are a few different ways that by studying the light from cosmic explosions, we can learn about the types of elements that are made, but I'm going to highlight just one of them now because it's most relevant for the JWST proposal. But the critical piece for our proposal is that all of these heavy elements in the periodic table, or most of them anyway, are radioactive. I showed you those beta decays that they were undergoing. So we can actually search for the light or the fading glow of the explosion that is caused by that radioactive decay and look at their properties. So I'm going to show you the example of a normal supernova. This is what the light curve of it might look like. So it's getting brighter on the vertical axis and then time on the horizontal. So even though a supernova explosion happens in a fraction of a second, we see light from those explosions for months. This is 120 days, and it'll continue past then. And the energy that is powering that is due to radioactive decay of the elements that are created in the explosion. So in this case, for a supernova, we can actually trace back down these decay rates that we are observing with time to what the main elements they synthesized are. In this case, large amounts of radioactive nickel, which decays to cobalt, which decays to iron. And we can see that in the light from the explosion if you can follow it long enough. However, this actually also highlights a problem. Namely, even if an ordinary supernova did create a tiny little bit of those heavy elements in the periodic table, we would probably never see it this way by looking at this fading glow of light for the radioactive decay. And that the reason is that normal supernova make several tenths of a solar mass of this radioactive nickel, whereas we're talking they maybe would produce a few thousandths of a solar mass of all those heavy elements combined. So essentially, even if they made those elements observationally, the light would be completely swamped by these iron peak elements, that it would be very hard to disentangle and actually see them. Whereas on the flip side, for neutron star mergers, we are expecting that the only elements they're creating, so all of that radioactive glow, would be due to these heavy elements. However, as I mentioned, those are incredibly rare. In fact, as of a couple years ago, we had never had a confirmed observation of a neutron star merger. So it was a little hard to rely on that when we weren't reliably finding them in the universe. And so that brings us to my next point. What the heck do gravitational waves have to do with any of this if we're just looking for the glow from explosions in the universe? And the key is that gravitational waves are incredibly important for this particular science case because they will actually help us find those neutron star mergers in the first place. As a really broad oversimplification, gravitational waves are the jiggling of space-time due to heavy objects that are moving. And as it turns out, pairs of very heavy objects like black holes or neutron stars that are orbiting each other, as this is a great demo, and I love the video of this, and it's just demonstrating if you have 2 objects, orbiting each other, they can create these waves or ripples in space-time that we can see. So neutron star mergers should be strong sources of gravitational waves. And this is why those of us who are astronomers studying explosions were incredibly excited when in 2015, Advanced LIGO gravitational wave detector turned on, and then in 2017 was joined by the Virgo detector in Italy, because they were going to have the promise of perhaps helping us find neutron star mergers. And in particular, while in 2015, LIGO first started finding massive black holes that were emerging, which are great, but don't really produce light, we don't think. In 2017, LIGO and Virgo did detect a gravitational wave signal from a very nearby neutron star merger. And that triggered quite a few events. So first of all, after a really intensive search that involved dozens of telescopes covering the whole globe and satellites in orbit, because the gravitational wave detectors only kind of tell you that this event happened in this patch of the sky that are, tens to hundreds of square degrees. So after they told us about it, we would search the sky looking for this event, and we did actually detect the fading light from that explosion. And that is what this particular graph is showing you. So the explosion we found from this 2017 event, its optical light, which is shown in blue, faded very quickly. It was gone within a matter of a week, but there was a slightly longer infrared transient that we followed for about 3 weeks afterwards. And it turns out when we added together all of this light, we found that the fading light from this neutron star merger decayed and faded at almost exactly the rate we would predict for all of those heavy, the radioactive decay of those heavy R process elements. So this event, GW170817, showed us that neutron star mergers do synthesize heavy elements in the periodic table. Now you might be wondering, wait, wasn't that the point of your proposal? Are you telling me that this is a solved problem even before JWST? But it turns out no, there still are open questions. And one of the big ones, there are a number of them, but one of the big ones is exactly how far up the periodic table do you actually go? There are a number of different simulations or models for neutron star mergers that have just slightly different physical conditions that predict very different things for how far up the periodic table and what elements you will synthesize. And this is just a graph showing you that, where it's just showing you relative abundances of different mass elements. And if you look at particularly the black, blue, and green lines, those are all the results of simulations of neutron star mergers that produce very different abundance patterns for different elements produced. And in particular, this blue one actually stops at a much lower mass number. It doesn't go all the way up the periodic table. But it turns on that early on, when you were observing neutron star mergers, in particular in those first 3 weeks, which are the only data we had from the 2017 event, all 3 of those models, which you see here have very different types of abundances and types of elements that they created of those heavy elements, they all look exactly the same, pretty much, and all agree with the data. And the reason for that is that you're observing this mesh of tons of different types of elements all at once. So you're looking at the sum of all of their different decays put together. So you can't really distinguish them. And it turns out this is an important question because it's really asking this question of, do you just go part of the way up the periodic table, or can you actually get to the heaviest elements down here? In particular for JWST, we still have this uncertainty about things like mercury. Can you actually make those in neutron star mergers? So as I wrap up in the next 2 minutes, there's the obvious question of what can JWST do? What is our proposal aiming to actually do to address this question? Well, it turns out that although all of those different predicted abundance patterns agree with this observation from 2017 over the first 3 weeks, if you were to extend these curves out to, say, 3 months past the explosion, you start to see very big differences. And that's because the later after the explosion you start to become more and more dominated by individual elements that have different radioactive decay timescales. And so you can see that these different patterns all spread, and you also have things that if you actually get up to the very heaviest elements, the actinides in the periodic table, you can actually get a little extra injection of energy from fission that can occur as well. So overall, our theoretical models show us that if you really get out to a few months post-explosion, things that looked almost identical early on are predicted to have brightnesses that vary by factors of 100 or more at those late times. So that's the goal of our program, is to, for another one of these programs, to trace the light over time, but really we are focusing on this time period from about 30 days to 120 days after the explosion. We're going to get several epochs of observations with JWST to try and probe how bright it is and how quickly it's fading to try and disentangle what elements were actually created in the explosion. So why do we need JWST? There's a couple reasons. The most important is that, these objects are incredibly faint. I actually laughed when Ryan mentioned 15th magnitude as potentially really faint. So these objects are much fainter than supernova, and they're going to be 100 to 10,000 times fainter 3 months after explosion than they were at peak. So we need to be able to probe down to magnitudes of like 27th or 28th in order to really make sure that we're constraining what this curve is and how they're actually fading with time. And the second is we need to reach those magnitudes in the infrared because the emission is also predicted to be very red. All of these heavy elements that are created have gazillions of electrons with lots of transitions, so they end up absorbing most of the blue light. And so it's predicted, these are a couple of predicted spectra, that they will peak somewhere, a few microns out to the mid-infrared. But the critical aspect of this is incredibly uncertain. Our theoretical models are not very good at understanding the physical conditions this late after one of these explosions. In particular, one data point we have from Spitzer, from the 2017 event, doesn't look anything like the models we have so far. So we are making use of the fact that JWST between NIRCam and MIRI has this incredibly wide wavelength coverage in the infrared, and we're going to cover as much of it as possible to make sure we collect as much of the light as possible to know that we actually are detecting what the decay really looks like. So in summary, our program, we're going to have a lot of fingers crossed throughout this. So what we're going to do once JWST launches and successfully commissions is we are going to wait and hope that the LIGO and Virgo, and now Conquer gravitational wave experiments, detect another neutron star merger nearby. Once they do, I'm very confident, again, fingers crossed, we are going to try and find the fading glow or explosion from that. Once we do, we will tell JWST to point at it and follow it for a few months afterwards, and then hopefully disentangle how far up the periodic table this actually went. Thank you very much, and I can take a few questions at this point.
Thank you so much for that talk. Wonderful. As people, if you have questions, please type them into the chat, or if you really want to talk, just tell me that and I will let you unmute as well. I guess what I really want to know is, do you have a sense of what your odds are of the one going off like in the first year, or is that just so unknown?
I mean, it is very unknown. Sort of our constraints from that do come from LIGO and Virgo have had a couple of observing runs so far. We had the one event in 2017, and then their third observing run, they detected about 5 neutron star mergers, all of which were far enough away that we unfortunately didn't detect the light from them, but there are decent constraints. Well, there are okay constraints on the rate of neutron star mergers from that, and we had to calculate this for the proposal, and we think there's probably about a 60% chance that in the first year in cycle 1, there will be an event that we can trigger this on.
That's pretty good. So then the first couple of years, it shouldn't be.
Yeah, exactly. So this was awarded long-term status, so it'll be active for both cycle 1 and 2 in the hopes of maximizing that it'll actually get triggered.
Spectacular. Okay, so then there's a question from Dick Shaw who says, supernovae are well known for being able to disperse synthesized elements into the ISM. What can you tell us about how efficiently neutron star mergers can disperse very heavy elements into the ISM?
Oh, that's an excellent question. And this is actually, this is a huge area of additional research as well. So there are a lot of different groups working on this. And part of what's interesting, so it does disperse this out. The material gets thrown out at very high velocities. Any individual neutron star merger might make a few tenths or hundredths, a few hundredths of a solar mass, maybe up to a tenth of these heavy elements. But what's tricky and that a lot of people are trying to understand is where those elements actually get placed. And this is part of the debate of why it's still uncertain if neutron star mergers are the only origin of these events, because this process of making 2 neutron stars, you undergo 2 different supernova, and those supernova have kicks associated with them that basically make the whole system start flying off in some direction. So it's expected that a lot of these systems are moving quite far. And so people who have actually studied short duration gamma ray bursts, which we also think come from either neutron star, black hole mergers, find that they're actually quite offset from their galaxies in a way that makes sense with the systems having been kicked. So a really active area of research is, well, even if they disperse this material, if a lot of these systems actually end up on the outskirts of their galaxies, can that actually be the origin of stuff that's dispersed within the ISM? So I don't have an answer for you other than that it's a really big open question. And one of the uncertainties is, are they all actually located too far out to explain everything that we see closer in?
That's very interesting. Okay, we have another question from Klaus Pontoppidan who says, is there an aspect of the JWST observations that will improve the measurement of the cosmic yield of elements through the R process, or is this more dependent on statistics of neutron star mergers from gravitational wave detections?
Okay, so basically, is it, yeah, I mean, I think this will help with the cosmic yield. Now, It always will then be tied to what are the actual statistics of neutron star mergers. It's going to be a while before we have, you know, many observations that we directly constrain. But one of the big uncertainties after the first event, where we do know it makes some of those heavy R process elements, is really this question of how unusual was that first event, or is it typical? So these are going to allow us to see, is the second event similar or not? And then really the question, the big open question, was what elements did that first one actually synthesize? Because there is this large degeneracy. So I think really allowing us to disentangle what physical conditions actually exist in the neutron star mergers, and so how far up the periodic table they go, will help us disentangle the cosmic yield in that process, because we sort of have a total quantity right now, but it's a little uncertain which elements that's distributed in, whereas this will help with that.
Great, thank you. We have another question from Jimmy Yoon, who asks, do black hole plus neutron star mergers also produce R process elements? If then, how are they different from the neutron star mergers, and could they be candidates as well?
Yes, that's a great question. And the answer is, it depends a little bit on things like what is the mass ratio between the neutron star and the black hole. But for certain mass ratios, you do expect that you will tidally disrupt that neutron star and fling out some material similarly. And so the main differences, though, is we actually predict that the elements that are created in the black hole neutron stars will be even more weighted towards the heavier elements in the periodic table. So if I actually go back to this plot, which showed you these different conditions that make, these are different conditions that basically say like how neutron rich is your material. So if your material is more neutron rich, you make the heavier elements, where if it's slightly less neutron rich, you stop at an earlier stage. And it turns out in neutron star mergers, there are actually a couple of different components to the ejecta. There are these tidal tails that are flung out, but you can also form an accretion disk that has a wind coming off of it. And you can have different conditions in each one that even are affected by things like, did you form a neutron star or a black hole in the center of the merger? Clearly, if it was a neutron star black hole, you have a black hole in the center. But essentially, while there are a couple of physical processes in neutron star mergers that actually allow you to make these physical conditions that would only yield the lighter ones, our understanding of the neutron star black holes is that you mostly just have those tidal tails, which we think physically should always get all the way up to these heaviest elements. So we think that they are good candidates, and they are likely even more weighted towards the heavier elements than the neutron star mergers are, which have a couple ways they could stop at lower levels because of the physical conditions in them. So they should probably be redder, essentially.